So we are back here again. So we have been discussing, I guess, kinetics, right? And in that context, we are trying to model different engineered or natural systems, engineered as in your activated sludge process, right? Or your flash mixer for that matter, right? Or any other engineered unit process, right? Or you can also look at how, what do we say, concentrations of various compounds change with time or distance in your natural systems, right? That's what people are always concerned about. So for that, we looked at the concept of defining systems as various reactors. So right, we looked at, I believe, batch reactors, continuously stirred tank reactors, and plug flow reactors, right? And we also looked at defining the concept of mass balance. So that's what we looked at in the previous session. So today we are going to look at how to apply the mass balance to these three sets of reactors, right? So let's go through, I guess. So what did we look at last time? A batch reactor. So that's what we are going to start discussing today. And the mass balance concept, mass balance, and the equation that we typically end up using is V dC by dt equal to Qn Cn minus Q out C out plus volume into rate of formation minus rate of loss. So whenever you are applying a mass balance, so there are three aspects that you need to look at, I guess. Let's see what they are, maybe a couple of aspects at least. So first, identify the material or compound. Identify the compound that you are trying to conduct the mass balance upon, right? So this is the first aspect now, always look at that. And the second major aspect is identify the system boundaries. So identify or define your system boundaries, right? For example, am I looking at this whole room, or am I looking at the whole building, or what are my system boundaries, or is it just about, let's say, 1 meter from the podium? So what are my system boundaries? Or is it let's say Haridwar to Roorkee stretch, or that includes, or is it from Rishikesh to Delhi, or what am I trying to look at, right? My system that I am concerned with. And then I am going to try to identify the kind of ideal reactor, identify the reactor system, right? And then apply mass balance. So again, major aspect is obviously identifying the compound, right? You are only going to apply mass balance on a particular compound, and then the what do we say, the key lies in identifying the system boundaries or the right system boundaries. So you will choose them based on what you want and also based on what is feasible to. So we will look at those later again. So the first aspect we are going to apply or the first kind of reactor we are going to apply the mass balance to is the batch reactor. So we talked about what a batch reactor is. It's a closed system that's obviously continuously stirred, right? Or continuous mixing, I guess, or completely mixing, but the key is that there is no flow coming in or going out. So I am going to apply this particular mass balance equation here, and what is that going to be here, please? V is the volume of my system here, right? These are the system boundaries here. So let's say I am conducting the particular mass balance on a compound A, which is being lost and transforming into B, I guess, right? And so here I am trying to identify my compound. So the first, it's A, compound A, and the second aspect is identifying the system boundaries, and that's something that I have done. Let's say it's the beaker in the lab. So identify the system boundaries, and then I identify the reactor system. So I see that obviously I know that it's a batch reactor, then apply the mass balance. So let's apply the mass balance. It's V dC by dt, right? C is now concentration of compound of A within the reactor, right? C obviously is the concentration of A within the reactor. V is your volume, is equal to, so now I have terms like Qn Cn minus Q out C out plus volume into rate of formation minus rate of loss. But obviously now this is a closed system, as in there is no flow coming in and there is no flow going out. So what does that mean? That means that the first two terms are irrelevant. So that's equal to just volume into rate of flow formation minus rate of loss of the compound. So that will more or less translate into dCA or dC by dt is equal to rate of formation minus rate of loss or R net. And in this case, I guess with the background that we have, what is R net equal to? I guess A is only being lost, so that's equal to minus K times concentration of A, right? And so I can now solve for the relevant equation, right? So again, but if you are just looking at batch reactor, what is the take home message? I guess this is the take home message for a batch reactor for a particular compound. dCA by dt or dC by dt is equal to R net. So in our example, we said A goes to B is the only reaction that we are looking at, but obviously if there are multiple reactions, let us say A going to C or D forming A and so on, you will write down the relevant R net or RF minus RL and you will get the relevant equation. So again, what is the take home message here for a mass balance for your batch reactor? dC by dt equal to rate of formation of the relevant compound minus rate of loss of that particular compound, right? So people make some petty mistakes in these cases when they calculate rate of formation and loss, but keep in mind that the rates always depend upon your reactants, right? So that's the key here. So now we are done with batch reactor. Let's move on to the plug flow reactor, right? So plug flow reactor, right? It's a flow system, right? So all the atoms or molecules that come through at the same point of time, they also exit at the same point of time, right? For example, A and B and C are here at a particular point time 0. So after time x, let us say, or time t1, pardon me, they will still be at the same lateral position A, B, C, right? And they will also exit at the same time A, B and C at time equal to t2, right? So there is no longitudinal mixing here, I guess, right? So anyway, a plug flow reactor, as we talked about, usually what do you say, engineered systems, yes, and also rivers, canals and so on. So let's look at applying this mass balance equation here. So what is this now? We are, let's say, trying to look at compound A that has relevant reactions, and then we need to identify the system boundaries. So system boundaries, and what's the issue here though? The issue here is that compound A, let's say, is coming in here and there are various reactions taking place, right? And by time here again the compound comes here, it is going to be at a lesser concentration. So let's say if A is decaying to B, right? So A is being lost during the course of this particular travel from this point to this point here, right? So what's happening to concentration? Let's say it's decreasing, let's say, yes, this is what I have, but here if it's concentration of A on the y axis, what is it changing with? Is it changing with x or time? So it's not changing with time, it's changing with distance, right? So this is one fundamental mistake most people make though. So as it travels down the along the course of the reactor, A, the concentration of A changes with distance, right? So people, I guess, say time, it's not time, at best you can call it or look at it by talking about hydraulic retention time. We are going to talk about what it is later. So keep in mind that in plug flow reactor, your particular variables change with distance and not with time, right? So that's something that you need to keep in mind, I guess, and we will see what it is about. So here now, as I know that it changes with time, with distance, pardon me, so I can't apply the mass balance over the entire system here, right? So what do I need to do? So there are two ways to go about it. So we'll look at both the aspects. So one is to choose a thin film within which the concentration is constant, right? But the concentration at this phase is Cz, let's say, and the concentration at the outlet phase is what shall I say, Cz plus Dz, okay, and the thickness of this particular film is Dz. Concentration at the inlet or this phase is Cz, C subscript Z, and concentration at the outlet phase or face is Cz plus Dz, right, and the thickness of this film is going to be Dz. And what was our initial mass balance equation, please? V dC by dt is equal to Q in C in minus Q out C out plus volume into rate of formation minus rate of loss, right. This is what we have. So, assuming that the flow does not change, obviously that is the case here, right. And what is V here? It is the cross sectional area of that particular what do we say film, or thus cross sectional area here, right. A into dz is my volume here, right, and dc by dt, right, is equal to q times, the q is constant, q in equal to q out. What is it at inlet? It is Cz, Ci equal to C inlet, right, is equal to Cz minus what is it at the outlet? Cz plus dz, right, plus volume again is A dz into rate of formation minus rate of loss, right. So, what do I have here? And again I divide here by A dz, I guess, right. So, dc by dt is equal to q by A dz, right. Let us say that is what I have here. And what else do I have here? Cz minus Cz plus dz, right, plus rate of formation minus rate of loss, right. So, this is what we have here, right. So, at steady state we can have the relevant what do we say transformations. So, first we are going to try to look at what this is here, right. And flow, what is flow? I guess q equal to cross sectional area into velocity, yes, hopefully that is right, yes, cross sectional area into velocity. So, how can I transform this particular set of variables? Q by A dz is equal to what now? Area into velocity, right, and again cross sectional area into dz, right. So, thus is going to be velocity by dz, right. So, what is distance by velocity though? What will that give you an idea about? That is going to be your time, and this in case is going to be hydraulic retention time, I guess, right. So, that is going to be equal to 1 by d theta, right. So, I guess I will do this over in the next page. So, what did we have here? So, dc by dt is equal to q by A dz, concentration at inlet minus concentration at outlet plus rate of formation minus rate of loss, right. So, and we just mentioned that q is equal to area into velocity by, and so q by A dz is equal to by A dz, and that is equal to u by dz, and that is equal to d 1 by d theta. And here we have a new term. What is theta now? Hydraulic retention time, right. That is what we have here. And so, thus transforms to dc by dt equal to d, and what is this here, I guess, minus dc, this is minus dc by d theta plus rate of formation minus rate of loss, right. And so, dc by dt plus dc by d theta is equal to rate of formation minus rate of loss, right. So, this is the equation for your plug flow reactor, right. So, at steady state, what is steady state? I guess there is no change in any variable with time. So, at steady state dc by dt will be equal to 0. So, now I will end up with dc by d theta is equal to rate of formation minus rate of loss of the particular compound, right. So, that is what I have here, yes. Again, this is the take home message, obviously at steady state, right. So, if you can look at the similarities with respect to what we derived for the batch reactor. So, this was for a plug flow reactor. For batch, what was it now? It was dc by dt is equal to rate of formation minus rate of loss. Again, so the difference here obviously is that it is for the plug flow it is not dc by dt, but dc by theta. theta is the hydraulic retention time, but again what does that give an idea about how it changes with distance, right? Because here we have 1 by d theta equal to u by dz, and what is z? Change with distance, right? So again keep in mind that for the plug flow, obviously the system the variable changes with distance, so that is what it means, right? So to simplify that further, let us say dc by d theta, right, equal to rate of formation minus rate of loss, or what is this equal to u into, or the velocity into dc by dz equal to rate of formation minus rate of loss. This is at steady state, obviously, right? U is the velocity there, and this is what we have. Yes. So this is one way to solve it from the relevant equation. So there is a much simpler way, obviously, and for that we need to have some background about the relevant what do you say, fundamental equation. So what was our fundamental mass balance equation, if you remember that, I guess dc by dt, right, plus u and del c is equal to diffusion coefficient into del square c plus sources or sinks, which are nothing but rate of formation minus rate of loss. This is the second way to derive what we just looked at. So neglecting diffusion here, neglecting diffusion, right, that means d del square c is equal to 0, right. So here what are we now left with? dc by dt plus u del c is equal to rate of formation minus rate of loss. So in a plug flow, I guess, right, the concentration is only changing with one dimension, let us say. So del, what is del? Del more or less, or del product gives us an idea about dou by dou x, dou by dou y and dou by dou z, right, del product. But if it is only changing with one dimension, what does this transform into? dc, let us say it is only changing in the x direction, let us say. So dc by dt plus u into dc by dx equal to rate of formation minus rate of loss, and we are done with our relevant equation, right. So this is similar to what we derived earlier. Again, what is this? I guess dc by dt plus dc by d theta, dc by d theta is equal to rate of formation minus rate of loss. So obviously if it's at steady state, right, means dc by dt equal to 0, and that ends up being dc by d theta is equal to rate of formation minus rate of loss. So that is what you see here, right. So again it is much easier if we have an understanding about the basic equation, but you can get by with looking at the other equation too. So again this can be applicable at steady state for any plug flow systems if you apply the, if you identify the system as plug flow, right. So we are done with that. So next aspect obviously, or the third kind of reactor is continuously stirred tank reactor, right. And what is this about? We have continuous flow coming in, we have continuous flow going out, right, and it is always either continuously stirred or completely mixed. So here the key is that we need to identify the variables. Let us do them now. So the flow coming in, flow going out, volume of the reactor, right, and concentration of the compound coming in, concentration of the compound going out, right, and then what else? And then concentration of your compound inside the reactor. So these are the variables that we are identifying, and we will see why they are relatively important, I guess, right. So now let us look at our mass balance equation. So V dc by dt is equal to q in Cn minus q out C out plus volume into rate of formation of the compound minus rate of loss of the compound, right. So this is what we have, yes. So let us try to transform this further. So we can have now, I guess, what is this please? dc by dt will be equal to, I am assuming q in is going to be equal to q out, right, in this case. If not, you can obviously look at that, equal to Cn minus C out plus volume into rate of formation minus rate of loss of your particular compound. So right, and this is what we have here, right. And what is q by v? Q is mass per what is it now, volume per time by volume. So, it is more or less time or hydraulic retention time, it is HRT or theta, right. Q by V will be 1 by theta, pardon me. Let me redo that, I guess. Q by V, Q is volume per time divided by volume, so that is equal to time, or what is it, HRT, 1 by HRT, pardon me again, right. So, that is equal to 1 by theta. So, what do we see here, dC by dt is equal to Cn minus C out by theta plus volume into rate of formation minus rate of loss, right. This is your fundamental equation. So, obviously at steady state, how is that going to transform into now, right. We are going to see that dC by dt is equal to 0. Steady state means there is no change in any variable with respect to time, right. So, let us see what that transforms into, and I take this particular term to the left hand side. So, C out minus Cn by theta is equal to, I guess, are we going to have the volume term if we are going to divide by V? So, we are not going to have the volume term here, right. It is going to be equal to rate of formation of the compound minus rate of loss of the compound. So, this is what we have for a CSTR, yes. And let us moving on, I guess, let us just rewrite this. So, the third case is for CSTR, what did we end up with, C out minus Cn, right, C out minus Cn by theta is equal to rate of formation minus rate of loss of your compound, I guess, right, C out minus. So, anyway, what is the take home message here, is there, this is obviously at steady state, yes, this is at steady state. So, what is the take home message here, you see that there is no differential, right, there is no differential equation here, it is just a usual equation, no differential equation here, and that, I guess, is relatively different from what we observed with respect to the batch reactor. So, let us write down what it is or what we looked at with respect to all the three cases, and we have now CSTR, right. And so, batch reactor we applied the relevant mass balance, and I believe we came up with dC by dt is equal to rate of formation minus rate of loss of your particular compound. For plug flow, we said, I believe it is going to be dC by dt plus dC by d theta, right, is equal to, going to be equal to rate of formation minus rate of loss. So, at steady state it is going to be equal to dC by d theta is equal to rate of formation minus rate of loss, and for CSTR, I guess we said it is going to be dC by dt plus C out minus Cn by theta is equal to rate of formation minus rate of loss. So, at steady state it is going to be C out minus Cn by theta is equal to rate of formation minus rate of loss, right. So, let us look at what this means. So, this is batch reactor, so obviously it is going to change with time. So, I have a compound here, right, compound A that is changing with time. So, whenever let us say someone says it is at steady state, what does that mean? So, that means there is no more change in your particular concentration. So, C versus T, when someone says there is no it is at steady state, it means that, right, it has already reached equilibrium, right. So, at steady state, what does that transform into now, dC by dt equal to 0, right. What does that mean? Rate of formation and will be equal to rate of loss, right, and you see no further change in concentration with time, right, and that is more or less your equilibrium. The system has reached the maximum extent possible there in your batch reactor. So, in the plug flow reactor, the take home message is that it does not change with it, as in the concentration does not change with time, but with the hydraulic retention time, or more specifically with the distance down the reactor now, right. That is what it means, keep that in mind, dz or dx, whichever dimension you are looking at. and CSTR at steady state you have no differential equation, right. It is just C out minus Cn by theta equal to rate of formation minus rate of loss. So with that I believe we will wrap up today's session, and we are going to talk about, I guess, the applications of these particular reactors to various kinds of reactions that we are will come across. So maybe for now, if we have enough time, let us look at one last example, I guess, right, with respect to the batch reactor. So let us say A goes to B, C plus A goes to B in a batch reactor, and I want to apply this to my mass balance let us say, right, or for now let us go with the simple first order equation, and we will be done with today once I am done with this particular case for batch reactor. And what is that going to be? I guess we know that it is dC by dt is equal to rate of formation minus rate of loss, right. And here rate of formation of the compound A, so I am applying the mass balance on compound A, these are my system boundaries, right, and it is completely mixed, and rate of formation of this particular compound, what is that? It is equal to 0, it is not being formed, and rate of loss of this compound is its stoichiometric quotient, which is 1 times what now, anyway it is negative, times rate of reaction 1, and that is equal to minus K1 rate constant times A, right. So what does dC by dt transform into? It transforms into rate of formation is 0 minus, okay, if I am already using negative here, I obviously do not need to use the negative term here again. So I guess this is something you need to be careful about. So if I am already having a sign here that indicates that rate of loss is being subtracted, I again am not going to look at the relevant sign here, but only the magnitude here. So rate of loss here is K1 times A, it is 0 minus K1 times concentration of A. So dC or d concentration of change of A with respect to time equal to minus K1 concentration of A, right, or if I say it is CT, let us say, if I am saying A is equal to CT, so dC right. So that integrate more or less CT by C naught equal to e power minus K1 into T, right, CT by C naught. And what does this mean, right, C and time exponential decay, guess not a good figure here, but that should do for now, right, and C naught is the initial concentration obviously, right. So I guess with that we are going to end today's session, and we will take this through with respect to the other reactors such as plug flow and batch reactor, and then look at a bit more of your complex systems, I guess. And that is it for now, and thank you.